Hello, my name's George, and this is my group project titled Increasing Safety on Public Bikes in Manchester. The project brief was to create a smart bike system, and our group's interpretation for that was to create a safety system for shared public bikes. So rather than focusing on bike performance, we focus on safety, and that's where our final concept combined helmet protection, helmet access, and the hygiene of that helmet, along with speed limiting as one interlinked system. The aim was to design a product to ensure and encourage helmet wearing in the use of public rentable bicycles. The objectives then split that aim into four main group tasks. One focused on helmet protection, which led to an airbag concept. Another focused on housing the helmet through a lockable access system. My chapter slotted in by sanitizing that helmet, and then the final objective was integration, interlocking all the systems together, including the speed limiter and system. It was clear that we were dealing with a system problem. Most people get public bikes out of convenience, and to further emphasise that point, 75% of rental bike users don't use helmets, as opposed to 29% of personal users do. Some shared bike systems do have helmets, but they're not used, and that's where my chapter slots in, because a sanitising system would make the helmet feel more usable, not just available. Due to great communication and teamwork throughout, the project felt like one complete system rather than 5 separate chapters. The first part was the mechanical helmet integrated access system, which links helmet removal to the bike hire process. My part was the sanitising spray system, which supports user trust by making the helmet feel more clean and reliable. The centrifugal speed limiter then adds that behavioural control, because the bike loses performance if the helmet isn't used. The airbag helmet improves crashing if the crash occurs, and the material selection chapter helps choose a material that's more workable and lightweight. As mentioned previously, the main problem was that barrier. Just because a helmet's available and says it's clean doesn't mean someone's going to want to wear it. They're still going to be thinking about the last person's sweat and hair. A dirty looking helmet like that may weaken the access system even if the actuation system works. So the main engineering problem became coverage. The helmet is curved and a lot of the inside parts are hard to get to. So the system needs to fit inside of the box. It needs to be simple and cheap for the shared public bike system. My aim was therefore to create a mechanically actuated spray system that improved internal helmet coverage and made shared helmet use more acceptable to everyone. The first part of the methodology was the geometry. I had to simplify the helmet design because the 3D scan attempts came out very patchy, even with LiDAR. The new helmet dimensions were 220mm by 170 with a depth of 85. To fit inside the box. Therefore, the envelope was pretty tight to work. I used an equation to work out optimal spray distance. With an 80-degree cone angle for most fine mist sprays, I calculated it to be around 131mm. This gave me a controlled starting point before my CFD simulation. Geometry was then moved into ANSYS Fluent. The simplified helmet was then subtracted from the box to produce an open air domain. I used a discrete phase model because I needed to know where the droplets contacted the inside of the helmet to prove that coverage. The mesh was then refined around the nozzle and the helmet surface because that's where I needed to apply the spray direction and surface impact. Completed a mesh independency check, and the medium mesh was accepted because the change dropped below 5%. These steps were then repeated for the geometries used to find more optimal coverage. Needed validating. I did a physical test with some dye and a paper-lined helmet to which the distance was set up as closely as possible to the CFD. This allowed me to compare the predicted spray path against what actually happened on a real service. I went to prototyping the design that would be integrated into the box. My initial prototypes was a single one and a button. See above me, you can see the final prototype. This stage linked that physical digital model into a practical system. Results, the single nozzle gave around a 20% coverage on CFD, which translated to a 28% estimated coverage in real life. Splitting the nozzles off both 40mm from the center and placing 150mm higher, the estimated coverage increased to 40% within the CFD to then 48% in real life. The main talking point is that the design improved, and both the CFD and real life experiments followed the same trend. One nozzle proved weak, showing weak upper coverage. However, the two nozzle system with different heights mitigated that issue, increasing overall coverage. It is important to note that there are limitations. The CFD simulation uses a very simple geometry, whereas the real life used the more intricate geometry, had tape connecting the paper together, so some droplets found it hard to connect. We can't claim full sanitization here, but it's fair to say that visible coverage increased and that the design slotted into the box perfectly. It's around a TR level of 3. I didn't prove full coverage, but there is a proof of concept there. To claim full coverage, I need a microbial swab test, UV tracer testing, and I need to have repeated cycle testing within lab conditions. So the design is at a concept stage, not and it's not a validated cleaning system just yet. Really well, achieving a proof of concept at a TRL level of 3. The brief wanted us to create a bike-mounted smart system, and that's what we did. We addressed a real issue and didn't just use theory. The strongest part was that each team member had physical evidence and something to show, and it all came together in government and around me. The main limitation is that the brief focused more on a bike-rider interaction, but we framed it as more of a safety. So the project was good, but to move up the TRL ranks, we'd have to do some real-life shared testing. Recommendations are towards the B network in Manchester, or just other shared bike systems for that matter. The recommendation would be to pilot it before you roll it out. So maybe little areas in Manchester, full city rollout, and then feedback, rather than a full city rollout. This would mitigate small issues before they become massive talking points. Then the hygiene, make it visible, put it on the app, put it on the box. Let people know if the box has been cleaned. Just develop it as the standard, so then you can put it on scooters. The world. Thank you very much.